Okay, Ahmed, be quiet, please. So, what we've got here in example 4, describe and explain the motion of a negative charged particle as it passes between the plates. So, what do we think is going to happen? We've had a look at one or two of these. It's going to go towards the positive, and what sort of shape of path would it take? A curved path is correct. So, let me just get the right pen, and we can draw that in. Where's my pen gone? Okay, so it's going to enter the electric field. And it's going to follow a curved path. And we could say that it will accelerate in the direction of the positively charged plate. And if you remember back to first year, the clue is unlike charges attract. Okay, and why does it accelerate? So as it gets closer, the attraction force increases. The closer it is, the greater the attraction, and that's why it starts to accelerate once it enters the field towards that plate. So I'll leave that on a second so we can all copy it. When we think of charges moving in an electric field, we can also think that charges move around electric wires. So if you had a wire, and remember when you've got a circuit, that would be the negative, that would be the positive terminal, the electrons will leave the negative and travel to the positive. When you have electrons flowing in a wire, naturally an electromagnetic field is generated around that wire. Okay, that is something that we discovered in 1819. If you were to put iron filings around the wire, they would fall onto field lines, creating a sort of circle. And if you were to put compass points, they would point in a circular path around the wire to show the electromagnetic field. So to fill in the conclusion, when electrical charges flow in a wire, a magnetic field is formed around it. The magnetic field lines form a cylinder around the wire. When the current stops flowing, the magnetic field disappears. You need the electrons to be moving for this to happen. You can increase the strength of the magnetic field by coiling the wire to form a coil, funnily enough. When you coil wire to increase the electromagnetic field around it, it's sometimes called a device, which is a solenoid. So on the left, we have a single wire, which is the red with the arrows. Okay, this is our single wire. Here, we've created a coil with the single wire. My pen's running out. There we go. And in creating that coil, we increase the strength of the magnetic field. So, how do we figure out which way the magnetic field goes? The direction of the field at a point is defined as the direction of the force on the north pole of a magnet placed at that point. To remember the direction of the magnetic field around current carrying wires, there are two simple guides called the left-hand rules and we're just going to have a look at how these work. So